So Scott, of course, is a leader in the field. He's a mentor to many young people, myself included. And I think he's directly responsible for a lot of the theory of quantum supremacy. And today he'll tell us about a next major step for the field, which is trying to find useful applications of the quantum supremacy experiment. Okay, so here's Scott.
All right, well, thank you so much, Bill, and it's great to be here. Shortly before civilization collapsed a few months ago, and we entered this freak branch of the wave function that we're now in, Google, of course, showed that using their 53-qubit programmable chip called Sycamore, they could take as input a description of a quantum circuit, call it C, and then they could quickly produce some samples, they call them S1 up to SK, from the output distribution of C. Now, of course, we can't directly test that they're from the output distribution, but we can check for consistency with that hypothesis using what Google called the linear cross entropy benchmark, or linear XEB. And this is a benchmark that I'll also be using throughout this talk. And what this simply means is that if you want to judge, the fidelity of a sort of quantum sampling experiment, you take each of the outputs that were produced, S1 up to SK, each of which in this case would be a 53-bit string, and then using your classical computer and brute force, you calculate for each one the ideal probability that the circuit C would have output S sub I, and then you just sum all of those probabilities up. And then you accept if and only if that sum exceeds a certain threshold. Okay, and the threshold has the form of B times K divided by 2 to the N, where here N is the number of qubits, here it's 53, for Sycamore. K is the number of samples, so the number of independent draws from the distribution. In the case of Google's experiment, that was about 5 million. Which they were able to do in just a few minutes, because it's only a few tens of microseconds per sample. B is a measure of the fidelity that basically we would like to be bounded above 1. And in the case of the Google experiment, they reported a B value of 1.002. So, slightly above 1. Okay, and this might look a little bit different from what was in Sergio's talk, but it's just a different way of presenting the same thing. Okay, and what does any of this mean? Okay, well, just to give you a sense for these numbers, if we just didn't have a quantum computer at all, and let's say we just produced a bunch of output strings, S1 up to SK, uniformly at random, with no knowledge of any quantum circuit or anything, well, even then, we would expect the average probability to be 2 to the minus n. So after all, this is a distribution over n-bit strings, right? So I add up k of those by linearity of expectation. I expect the sum to be about k over 2 to the n. So in other words, I expect to achieve a value b equals 1, could say. Okay, now what about with a perfect and noiseless quantum computer? Well, there it's just a little calculation. It was an integral that, fortunately, despite being a computer scientist, even I remembered how to do. And you do the integral, you get the value of 2. Assuming that, as we expect, that a random quantum circuit gives you a sort of Porter-Thomas type of distribution, you then expect the sum to be about 2 times k over 2 to the n, twice the classical value. Now, the key point is that we do not know of any polynomial time classical algorithm that would spoof these samples, that would produce samples S1 up to SK, given the circuit C, in a way that would achieve a B value that was even slightly bounded above 1, like 1.00001, for example, or even 1 plus 2 to the minus n. Not even that do we know how to achieve classically. Okay. Now, can we prove that there's no such algorithm? Well, of course we can't. We can't even prove that P is different from P space, or, all kinds of more basic things than that. We would love to be able to prove that if there were such an algorithm, then the polynomial hierarchy would collapse. but for reasons that were discussed in the previous two talks, we don't know how to do that either. But in a paper a few years ago with Weijie Chen, and in a more recent paper with Sam Gunn, we were able to give some modest complexity theoretic evidence against such an algorithm. Namely, we were able to show that if there were such a classical algorithm, then you would also get a fast classical algorithm that could estimate certain, like the probability of a particular output in a random quantum circuit with variance that's slightly better than what the trivial estimator would achieve. Okay, and I don't know that that's impossible, but at any rate, it would have some consequence for sort of our ability to classically simulate quantum circuits that is not just about spoofing a sampling problem. Okay, so then the question is, so Google reported B equals 1.002. So is this a proof of quantum supremacy? Well, as everyone knows, there has been a debate about that question. I mean, I think that it is fair to say, if you look at Preskel's paper from 2012, what he meant by quantum supremacy, that that it has been achieved, keeping in mind that this is something that can be achieved and then unachieved later if someone discovers a better classical algorithm. Okay, but there has been some dispute. Now the central drawback of the current sampling supremacy experiment is that as far as we know today, even just to verify the samples with a classical computer takes 2 to the n time, just like classical spoofing takes, right? So there's sort of a cat and mouse game between the two. You could say, if n, your number of qubits, is small enough for verifying, well, then maybe it's also small enough for spoofing to be practical, right? And this was sort of, this point was at the heart of IBM's response paper that they put out, where they tried to rebut Google's claim, where they said, look, if we used Summit, it has 250 petabytes of hard disk, and using that, we could just explicitly store the entire state of the 53 qubit Sycamore chip to hard disk and thereby simulate it in just a few days. It sounds from Sergio's talk like Johnny Gray's recent results would give an alternative way to do that. Of course, this has not been actually demonstrated yet, but let's take it that something like that would plausibly work. Well, okay, then you could say there's still a gap in that the quantum computer is producing outputs in a matter of a few minutes, where verifying them took days. So we still have some gap there, but of course we would like some experiment, of some NISQ sampling experiment where we could do the verification efficiently. I mean, that I regard as the biggest theoretical open problem in this whole area right now. Okay, but now having said that, maybe the most fundamental objection that people raised to the supremacy experiment, and that I had to answer to journalists and on my blog and elsewhere, was, well, what are such experiments good for? So trying to make a list of what the sampling-based quantum supremacy experiment is good for. Well, it is good for disproving the people like Gil Kalai, who said that quantum computing speedups were impossible in our universe. That's number one. Number two, well, it's hard to think of number two. No, I mean, it's good for device calibration, as Sergio talked about. It is good for sort of various, internal engineering goals. But, is it good for any actual application? And, that has been, one of the biggest unknowns in this area. Okay, so now this leads to an idea, a thought that I had a couple of years ago, which was that, well, maybe there is something that you can use this type of sampling experiment for. It just generates a bunch of bits that are mostly random, and that sounds pretty useless unless random bits are actually what you want. And then maybe it could be useful. Okay, so in particular, let's consider the problem of generating bits that we can show to be random under some plausible computational assumptions. Okay, so of course, if we believe quantum mechanics, then it is trivial to generate as many random bits as you want, using all sorts of quantum mechanical apparatus or radioactive decay or whatever. You can buy devices online or go to websites that will claim to generate quantum mechanical random numbers for you. Okay, but suppose that we need a public source of random bits that are going to be placed on the internet, and that everyone has to be able to download and trust as being really random, even though they don't know, what hardware is being used to generate it. Can we do that? Okay. Well, the observation I made was that once you can get a sampling-based supremacy experiment like Google's to work, then almost immediately you can repurpose it for a sort of protocol in which a classical challenger who starts with a small pseudo-random seed would generate some challenges, send those challenges to a quantum computer, demand back responses within a very short time, and then verify those responses at its leisure and using classical brute force. And then if the responses pass the verification, then under some computational assumption, you would have some guarantee that the responses must have had at least such and such entropy, such and such min entropy. Okay. Now, is that useful for anything? Well, there are all sorts of applications where you want a public source of trusted randomness. An example being proof of stake cryptocurrencies, like the next generation Ethereum supposed to be. Okay, that would replace the sort of massive, wastage of energy of Bitcoin by something else, but the something else requires a large public, trusted randomness source. Okay, having said that, there are a lot of issues in actually making this practical. In particular, can it be acceptably secure in practice? Can it be spoofed? By with sort of reasonable expenditure on the part of the adversary. And of course, it has to be compared to all the alternatives, which the ideas for public randomness could range from using the last digits of the Dow Jones Industrial Average. I don't know if you want to use that right now. Maybe it's too, erratic. But or to using the pattern of granules that would form on the surface of the sun. Okay, there's all sorts of places in the world where you could look for public randomness. This would have to compete against all sorts of other things. So I don't know if it will be useful in practice, but the claim that I'll make for it is that at least this protocol sort of refutes the statement that it is obvious that sampling on NISC quantum computers has zero application to anything. Okay, it refutes the obviousness of the inapplicability. Okay, so okay, so what is the protocol? Well, basically, it involves a classical client which generates quantum circuits on n qubits, call the circuit C1 up to Ct. It generates them pseudo-randomly, so in a way that would mimic a truly random ensemble. Then at each round, little t in the protocol, the client sends the most recent circuit, C sub t, over to the quantum computer server. And it demands back a response, which we'll call S sub t, within a very short time, like say a second. Okay. Now, in the honest case, that response would simply be a list of k independent samples from the output distribution that you get by applying C sub t to the all zero initial state and then measuring in the computational basis. Okay, then next, the client, using its tiny seed randomness, picks a few random iterations, and for each of those iterations, it just goes and invests the brute force to calculate the linear cross entropy score for those iterations and make sure that it gets a score that's bounded above 1, like a signature of quantum behavior. Okay, now if it does, if the test passed, then you get some lower bound from the analysis on the amount of min entropy that has to be there in all of the samples concatenated together. under some computational assumptions. You don't know where the entropy is, but you can take all the samples and you can then feed them into a known tool, a classical randomness extractor, such as the so-called GUV extractor, in order to get out nearly pure random bits that you could then use for some cryptographic application. Okay, now the central point that I wanted to focus on in the rest of this talk is kind of the main conceptual point behind the whole scheme, which is why must there be any entropy whatsoever in the server's responses? That is, how do we know that even if the server has to be a quantum computer, it's not a quantum computer that just answers each challenge in a secretly deterministic way. All right, well, I want to give you some sense for how the argument goes. So what we do is we suppose to the contrary that there is some function f, in BQP, so efficiently computable by a quantum computer, such that the samples returned s, is just equal to f of c. It's just a function of the circuit that it's given. Okay, we want to show that if a secret deterministic such function existed, then this would imply some strange computational powers on the part of somebody. Okay, so like in all complexity theory, we have to start from some problem that we're assuming to be hard. So I'm going to give you a somewhat strange problem, which I call long list quantum supremacy verification, LLQSV. It needs a better name. But this is the following problem. You are given Oracle access, or if you like, random access to a gigantic list of random quantum circuits, C1 up to Cm. Okay, and by gigantic, I mean m is exponentially large. Okay, like it's 10 to the n power or something. You're also given a bunch of n-bit strings, S1 up to Sm, n being the number of qubits of each circuit. Okay, now you're asked to distinguish two cases. Case one is that each S sub I was sampled just uniformly at random. Case two is that each S sub I was sampled from the output distribution of the corresponding C sub I. Okay, was that clear? We want to distinguish these two cases. So, and I want you to think of, this problem, yeah, it seems pretty hard. I mean, you could do it in Sharp-P or something, but it seems hard even if you had a quantum computer that could access this gigantic oracle. Okay, well, I'm going to stick my neck out a little bit further, conjecture that there's sort of no AM protocol for this problem. And the key claim is that if there were a quantum computer that could pass the linear cross entropy test in a secretly deterministic way, then there would be a QCAM protocol for LLQSV. Okay, where here QCAM means quantum classical Merlin Arthur. So it's just AM with a classical Merlin and a quantum Arthur who can verify the response. Okay, so now why would we get such a QCAM protocol? Well, intuitively, the whole problem just boils down to approximate counting. In other words, we have this exponentially long list of circuits and purported samples from the circuits. And now, it suffices if we can just estimate how many i's are there in our gigantic list such that f of c sub I equals s sub I. Okay, so, we're trying to, that this is an exponentially small subset, but, with the help of a Merlin, we could do approximate counting to try to lower bound the size of this subset and figure out, are there sort of more circuits than we would expect in the purely random case for which, the sample that is there is actually what the function f produces when you run it on that circuit. Okay, so, so the standard approximate counting trick of, Goldwasser-Sipser or Stockmeyer and so on, Arthur would just send Merlin a random hash function, a G, and demand that Merlin send back an index I such that f of c sub I equals s sub I, and also I hashes to some particular value, like the all 0, 1, under that hash function G. Okay, So you can do approximate counting to sort of check that you're in the yes case, the case of valid sampling. Now, as an observation, notice that if our circuits C sub I were all classical, then there actually would be an AM protocol to solve this problem, right? Because a classical circuit has the property of being reproducible. You can always just get the same output over and over by rerunning it with the same input condition. Even if it has randomness, you could just fix the random bits that it uses. Okay, so this is one way of understanding why quantum computation is actually important for this argument and for this randomness protocol more generally. Okay, now the more technical part is how do you show that in each round of this protocol, you're not just getting, let's say, one random bit or 0.1 random bits or some tiny amount of randomness, but you're actually getting omega of n random bits. So an amount that scales like the number of qubits in your circuit. The way we do that, we have to design a rather more complicated AM protocol. Okay, but we say, suppose you had a BQP machine, call it M, that sampled S, that list of samples, from a probability distribution that had two properties. One, it put a large mass, like at least Q, on samples that passed the linear cross-entropy test. And two, it put a large mass, like at least P, on samples that have a big weight. So like they're sort of heavy. They're not good in terms of min entropy. They've got like min entropy of only H. They've got probability of 2 to the minus H, where say H is less than N. Okay, and then also suppose that B and P and Q are big enough. Then there is an AM protocol for this LLQSV problem with a quantum verifier running in time about 2 to the H over 2, and also with a small advice string. Okay, the intuition for this is that Merlin is going to point Arthur to those circuits C sub I for which that quantum algorithm M outputs the string S sub I with a large probability, at least 2 to the minus H. And then knowing those circuits, Arthur can then use Grover search to check Merlin's claims, which will take, amplitude amplification will take about 2 to the H over 2 times in that case. Okay, now when you try to design this QCAM protocol, the central difficulty, in a sense, is that Merlin is trying to convince Arthur of statements like, that algorithm M on the circuit C sub I outputs the string S sub I with probability at least 2 to the minus H. Okay, well, the problem is by itself, that's just not going to work. Because, what if that probability was right near the threshold of 2 to the minus H, right? You can't, exactly calculate the probability. Okay, so you say, all right, so allow some leeway. Let's say that Merlin only needs to convince Arthur that the probability is at least 1 minus epsilon over 2 to the H. But then the problem is as soon as you allow that leeway, well, then, that could destroy the soundness because maybe there are vastly more circuits where C sub I outputs S sub I with probability 1 minus epsilon, over 2 to the H. So then, and once you've lowered the bar to that, well, then a cheating Merlin could sneak in 1 minus 2 epsilon, acceptors and so on. So, you would seem to get an infinite regress. So you need some definite place to stick your threshold where you'll get a good gap between completeness and soundness. And in some sense, the main thing that I had to show in the theoretical analysis is that there is such a threshold. So basically that there is going to be some epsilon less than a half, such that there's a large gap between, how well between completeness and soundness. So how well Merlin can do, getting you to accept the 1 minus epsilon over 2 to the H in the yes case, and how well he could do getting you to accept slightly less probable than that output strings in the no case. And then once you know that epsilon, you can hardwire it in as part of the advice, as a tiny bit of advice to the AM protocol. Okay, so when you work out all the parameters to try to get the rate of randomness generation from this scheme, basically what you get is so L, which is some hardness parameter, which would be at most n over 2, where n is the number of qubits in your quantum computer. and then times some quantity, which looks like b times q minus 1 divided by b minus 1, where b is that threshold parameter for the linear cross entropy test, and q is the observed success probability of the quantum computer at actually passing the linear cross entropy test. Okay, so basically, you need b times q to be larger than 1 to have any, for this protocol to work at all, to get any rate of random bit generation. And this kind of determines, your physical hardware requirements. Basically, as your hardware is noisier, then you need, then that's going to lower your success probability q. Then to get b times q greater than 1, then you need a larger b. Okay, but then, if I set the threshold higher, that's going to decrease my success probability even more. So that sounds really bad. The escape route is that I can set b to be just slightly larger than 1, in particular to about 1 plus delta, where delta is the quantum computer's fidelity. And then I can take a large number of samples. So I'll ask for like k samples, where k is like 1 over delta squared. And then I appeal to the law of large numbers. So not surprisingly, the noisier my quantum computer, the more samples I need in order to get the same amount of entropy out. Okay, and there are a few remaining parts of the analysis, like you have to show that generating the challenge circuit pseudo-randomly is okay under some further hardness assumption. You need to show, the hardest part is you need to show that the entropy actually accumulates from one round of the circuit to the other, that there's not some weird conspiratorial correlations that would keep the entropy from growing. For that, I used a combinatorial lemma due to Roan pellet, among lots of other ingredients. Okay, now let me just tell you what I think is the biggest challenge for this protocol and for really making it useful. The biggest challenge, well, it's something I mentioned before, that is to find a way to make the verification efficient. That is, so that it can be done in time polynomial in n rather than 2 to the n. The trouble is that until one does that, there will always be a cat and mouse game between the verifier and the spoofer. So, if the verification time and the spoofing time are both of order 2 to the n, right? Then you're limited to, let's say, 60 qubits or 65 qubits, whatever, and then maybe spoofing could be done. Now, what gives some hope is that the verification, as I said, needs to be done only a tiny random sample of the round. So it needs to be done only very, very occasionally and at the verifier's leisure. Whereas the spoofing, to be successful, would have to happen over and over and over again. So if you had a quantum computer that could do 1 round per second, well, then the spoofing with your classical computer would also have to happen once per second. Okay. But on the other hand, the spoofer could always buy more hardware. They could parallelize. Maybe they could even spend, billions of dollars to buy, I don't know, however many petabytes of RAM to do, like the Summit machine, but in RAM, right? So, you're always kind of worried about that kind of thing. Okay, now in principle, we know that this kind of problem can be solved because of the beautiful protocol from a couple years ago by Brikursky, Cristiano, Mahadev, Vidic, and Vazirani. So they gave a completely different scheme for generating certified random bits with a quantum computer. Their scheme has efficient verification. It is based on cryptography, based on LWE. Okay, unfortunately, I think it remains unclear whether that scheme can be practical in the NISQ era. So the central problem, if you like, is can we get efficient verification and NISQiness at the same time? Okay, and that's a question for certified randomness schemes in particular. It's also a question for just any application of NISQ quantum computers, more generally. Okay, there are lots of other interesting challenges. Like, can one get more and more certified randomness by reusing the same circuit over and over? That would make the protocol much more efficient. Could we get soundness under less boutique complexity assumptions? Can we get soundness even against adversaries that are entangled with the quantum computer? And how, are there good protocols to solve the problem of, well, why should anybody else trust the verifier? And why should they trust the secret seed that is being used by the verifier to generate the challenges? or indeed the large verification computations that the verifier has to do. So let me stop there, and thanks a lot for your attention.
Okay, great.
And I'm sorry we've run into overtime, but I am happy to take any questions.